Dispersion. Dispersion is a phenomena that occurs inside the optical fiber mainly because of the broadening of the digital pulses. So basically, the broadening of pulses is the major effect of the dispersion. So we have some optical pulse, highly shaped optical pulse that is transmitted from the transmitter, and after passing through a long distance, the pulse would change its shape, and also its peak value will also decrease. At the same time, its on time or pulse duration will be increased like this. So at the destination, you will see that the amount of power, peak power contained by the pulse is reduced. At the same time, the on time becomes very large. So this is the phenomena that we have to understand in connection with optical fiber propagation, light wave propagation through optical fiber. So there are various mechanisms present for dispersion. One is the modal, or sometimes it is called the intermodal dispersion. Another is the chromatic dispersion. Another is the polarization mode dispersion. Now, what is the effect of pulse broadening? The major effect of pulse broadening is the reduction of data rate. That is the bandwidth limitation. Okay. So consider we want to transmit a signal 101. This is the data. So 1 is transmitted through this via this pulse. 0, for 0 we don't have any pulse, and for the next one we have this pulse, right? And we are assuming this is the detection threshold, right? So at the transmitter you can see for logic 1 pulses the power is much higher compared to the detection threshold, so there was no problem. Now what happens after passing through several kilometers of distance, right? There will be some dispersion. So pulses will be broadened. At the same time, the height of the pulses will be reduced, right? So as you can see, originally here it was 0 originally, right? But after passing several kilometers of distance, this portion will now carry some power, right? Because the pulse has been broadened. Since the pulse has broadened, so there will be some power, right? Now after passing some more kilometer distance, you will see intersymbol interference is there. So the height is again reduced, these two heights, but originally it was 0, right? Originally it was 0, there was no power, but at this position now we have sufficient amount of power, right? So ISI is taken place. One symbol is interfering with the others, but if we allow the fiber to pass to carry the signal even for the distance, then you will see that it may happen that those logic 1 pulses, power contained by the logic 1 pulses may be lesser than the threshold, and it may happen that power contained for this region becomes higher than the threshold. So we have complete distortion. Okay. Now for no overlapping of light pulses down on an optical fiber link, the digital bitrate BT B suffix t must be less than the reciprocal of the broadened pulse duration, that is 2 tau. So BT may be less than equal to 1 by 2 tau. This assumes that the pulse broadening due to dispersion on the channel is tau, which dictates the input pulse duration, which is also tau. Hence, a conservative estimate of the maximum bit rate that may be obtained on an optical fiber link is 1 by twice tau. So this is another way of looking the dispersion that we have already said with another kind of data. So we have this is the transmitter part. So after passing several kilometers of distance, we have some overlapping, right? And after uh, passing even further distance, it becomes complete mess. Okay, so everything will be lost. We cannot recover the original data properly. Now, more accurate estimate of maximum bit rate for an optical channel with dispersion may be obtained by considering the light pulses at the output to have a Gaussian shape with an RMS width of sigma. So maximum bit rate can be calculated as, maximum bit rate means BT max equal to nearly equal to 0.2 divided by sigma bits per second. So this is another way of estimation of the maximum bit rate.